Hello GGS300, welcome back to what is going to be the third lecture of GGS300 Quantitative Methods for Spatial Science. Today I'm going to be focusing on descriptive statistics. Okay, so the second assignment is going to be set from this lecture. The second assignment will be up on Blackboard as per usual. You just need to complete it. Make sure you put any graphs you generate into your document. Make sure you answer the questions. Make sure you copy your code in there, make it into a PDF, and then resubmit it into Blackboard, okay? I've had a few questions from you. Actually, I've had quite a lot of questions from you, but that's all good. I'm happy about that. It shows that you're engaged with the work. I take this as a good sign. Reach out to me if you've got any other further queries, and let me know if there's any issues. Okay, so the point of today's presentation is to introduce you to descriptive statistic concepts and techniques. And in fact, many of you, if you've already done a basic stats module, will be familiar with many of these kind of descriptive statistical metrics that we're going to use today. And what's kind of exciting is it lays the groundwork for what we're going to do next week, which is actually spatial descriptive statistics. Okay, so this week kind of doing the classical statistics metrics, and next week we'll start to move into that kind of spatial domain a bit more. Okay, so what are descriptive statistics? Well, essentially these are those types of statistics that provide a numerical or quantitative summary for a data set for the different characteristics that the data in that data set may actually have, okay? And basically there are underlying statistical properties which allow us to kind of understand more about how processes take place. So in this case, we're going to be talking a lot about distributions, variation within data, things like this. So what do these two things have in common? So one is a set of height measurements. So imagine we take everyone in the class and we line everyone up, me included, and then we essentially measure how high everyone is, and then we basically have a distribution of heights. But what happens if we have two die, and essentially we stand there and we roll them 36 times, for example, or 50 times or whatever, and each time we measure what the actual score is. Well, if you haven't already figured this out, for those of you who maybe you've already kind of engaged with this topic before, these types of processes essentially display what we call a normal distribution. So essentially we will have many more values that are around the mean of the data set than we have in the tails, okay? And that's how we end up with this type of normal distribution shape that we have here. So it's called a bell-shaped curve. You'll see on the left-hand side where there are height measurements, which represents this kind of the fact that we can measure data, whatever it is, whether it's, you know, car speeds or heights or dice, and very often essentially they display this distribution property, and we're actually able to use that with it to our advantage in statistics, and that's kind of where we're going to be going today. All right, so I think the key point is when you think about, for example, the normal distribution, as you see here on the left with height measurements, when you see that shape of the curve, the bell-shaped curve, just think of that in terms of there are data values underneath it. And essentially what we're doing is we're drawing a line through the peaks of those data values. So you remember that we worked with histograms in previous lectures and in previous labs. And as a consequence, now we're kind of moving on a bit further to understand distributions, so quite similar to histograms. But just imagine that line drawn across the top is just tracking the very top of those histogram bars, okay? Great. And on the right-hand side here, you know, we're thinking about that shape in terms of the number combinations. So for example, whereas it was with heights before on the x-axis on the left-hand side, so most people in that data set were around 65 inches. On the right-hand side here, it's actually the summation of those die each time that we roll the die. And actually 7, when you're rolling 2 die, is going to be the mean. And actually it would be unlikely that you would get a 12 or a 2 very often, because you don't need to have a smaller probability of landing those numbers which would sum up to those values, okay? Whereas there are a greater number of combinations in the middle of the distribution that could sum up to those values, okay? And that's how you end up with that shape. But actually on the y-axis, what's nice about this on the right-hand side is actually put a probability in there. So it's putting a probability on you if you roll the 2 die, what the probability is of you actually getting that particular outcome, and you're able to actually get that probability based on the distribution of the data here. So I've mentioned this a couple of times in the previous lectures. I'm going to mention it again quite a lot over the coming weeks, that you're able to take empirical data that we've measured through observation, and then we're actually able to say, well, now I know what the distribution of the past data is, I can make a prediction about the future based on the distribution pattern. And that's basically, I say that's where the money is. I mean, that's both metaphorical in terms of where the interesting stuff takes place in statistics, is also literal in terms of the economy. If you can do forecasting, if you can do predictive analytics of basically anything, then you're guaranteed a more secure job, potentially a better paid job, and therefore it's generally a good skill set to have. So I raised this before, that this is kind of my take on how we do spatial scientific, how we undertake spatial science, basically. And on the left-hand side here, what we have is the descriptive statistics part. So we're able to collect and gather data, process it, and then we can reach some conclusions about that data, basically. So this is the first third of the course. It's different from what we're going to do in the second third and the final third of the course, where we're basically focusing on inferential statistics. But you'll notice that I mentioned about the shape of those distributions and the probability associated with different parts of that distribution. That's basically going to become one of the bedrock techniques that then we use when we get to inferential statistics. So the likelihood of us taking a sample and where the mean of that sample may be in relation to the rest of that population is kind of a fundamental part of then how we start to draw conclusions in statistics. Okay, so let's just move on now. We have some definitions that we just need to cover, and one is parameters versus statistics. So in this case, when we talk about parameters, we're actually talking about the whole population, whereas when we talk about statistics, we're really talking about a sample of the population that we might have taken in some way. Okay, we also denote these differently. So for example, if we take the population mean, we're going to have mu as the Greek letter that we use to denote that, or we use the capital letter N if we're talking about the population size. Equally, if we talk about the sample mean, we're going to be talking about X bar, as we see down here, or we're going to be talking about the sample size in terms of little n, okay, lowercase n. Okay, so we'll move on now. Descriptive statistics. So we're going to have these three different types of descriptive statistics that we're going to be covering today. So we're going to focus on, firstly, the central tendency. So these are single metrics which basically describe the distribution of data that we may be examining. Number two, we've got measures of dispersion. So this is basically, think about the variability within the data, how far distributed the data points are. And then in the final case, we're going to be thinking about the shape or the relative position of the distribution of the data. Okay, so in the first case, central tendency, we're talking about the mode, the mean. In the measures of dispersion, we're going to be talking about things like the range, the standard deviation, the coefficient of variation. And then finally, for shape and relative position, we're going to be talking about the skew of the data, so how symmetric the distribution of the data actually is, or the kurtosis of the data, so how peaked or flat the distribution of the data actually is. Okay, so if you're not familiar with any of those terms, don't worry, I'm going to cover them now. So let's start with some easy metrics, which some of you may have encountered before. So we're going to start with the mode. So the mode is quite simple. It's just merely the most frequently occurring value that we have within our data set. So if we have a data set which contains 10, 20, 20, 15, 15, 20, 25, then the most frequently occurring value is 20, and therefore that's the mode, okay? And this is a unimodal data set, which could be described also for the bottom left-hand part of the slide here. This is also unimodal, but it doesn't mean that we don't have either bimodal, where we have two peaks, so just like this one here on the right-hand side, or multimodal data sets, where maybe we have lots of individual modes within the data for a variety of reasons. And really, this is indicative of a process that's happening. It doesn't help you understand why that's happening, and that's why you may need further statistics to try and understand exactly why you're getting these frequent values at these particular points. Okay, so that basically indicates the most frequent value, and it's basically at the local maximum in the chart. The median, so imagine if we just ranked all of the data points within our data set, the median would basically be the middle value in that ranked sorted data set. Okay, so we can calculate this in a variety of ways, as I'll show later when we get to our studios, multiple ways to calculate it, but we're pretty much always ordering the data from smallest to largest, and then if the number of data sample points that we have is odd, we can just take the middle value. Or if the actual number of data sample points in our data set is even, then what we need to do is we need to find the two values in the very middle of the distribution, then take the average of those two values. So this is fairly easy to understand still. There's nothing too complicated here, and we'll be able in the R lab to actually go through how we do these particular calculations. And when I think about distribution, one of the things that I want us to think about is the distribution of household incomes, for example, because that enables us to kind of relate it to something that we think about, or relate it to something meaningful for us. Okay, so here we've got a good example of a distribution that's heavily skewed. It's positively skewed, so the distribution of values is skewing all the way to the right-hand side here, increasing in size. But it gives us some good understanding for why some metrics might be better than others at describing the underlying distribution. So using the mean to describe a distribution this skewed is probably not a great metric to use, because basically all of those high incomes that we see over here off the corner of the screen basically skew that number to be very, very high. So the Bill Gates of the world, the Jeff Bezoses of the world, the Elon Musks of the world basically massively pull that average number up. Whereas if we actually use the median, what we're doing there is we're taking the very center of the very central data point in the whole distribution, and that arguably is a much better way to capture the kind of true range of the kind of true distribution, a more representative distribution of all of those household incomes. Okay. And then let's move on to the mean. So, I mean, you will be familiar with this, I assume, already. So this is just the average, the arithmetic mean. So it's just the sum of all of the values and then divided by the number of values. So we can get the mean for the sample, as we see here on the right-hand side. So to get x bar, we need to sum all of the xi values that we get and divide it by so lowercase n. So that's the number of data points in the sample. Or we can get the population mean, mu. So essentially to get mu, we need to, again, sum all of those data points that we have in the population, but then we divide it by, notationally this is different, but it's uppercase N referring to the whole population. So it's the same math, but essentially we are doing, we're just displaying it differently to indicate that we are drawing these data points from different groupings. So one from the sample, one from the population. The weighted mean, okay, so maybe we only have data, so let's say that we have the temperature data by month, okay, and that means that we don't have the daily temperature, we just have an average temperature for the day. What we might want to do if we then wanted to get the average temperature for the year is actually weight the contribution of each of those monthly temperatures based on the number of days that we've got in each month, so that it provides an overall, it provides a weighted contribution to the overall metric. Okay, so we'll do this in the lab. Essentially, it's not too complicated. In order to get that weighted mean, essentially all we're doing is we're multiplying the average value that we get, such as the temperature, temperature across the temperature of the day, the mean daily temperature per month, my apologies, multiplied by the number of days that we have each month. Okay, so that's the frequency count for the group. And that's how we get the numerator here. So it's the sum of xj times by fj. And then what we need to do is need to divide it by the total number of values that we have within our group. Okay, so this is the weighted mean. We'll cover it within the lab. It's not that complicated, and you can think of it, for example, in terms of taking a monthly temperature and then converting it to an annual temperature. So I think at the top here, I've just basically described the example for how we would think about it in terms of temperature. So maybe we've got the daily average for DC over the summer months, but we want the daily average for the entire span. So we're able to say that it's 76.2 Fahrenheit on average for 30 days, and then it's 80.7 Fahrenheit on average for 31 days, and then it's 81 Fahrenheit for 31 days. So we need to multiply them and then sum them all up, and then we need to divide by the number of data points that we have, which is 30 plus 31 plus 31, and then when we do that, we end up, when you follow this calculation through here, with 79.3 Fahrenheit on average over the summer months in DC. Okay. I think I'll probably keep returning to this next example because I think I use it quite a bit in the course, and this is actually if we wanted to look at home values in a city block, then maybe we want to use a weighted mean. So I will use home values through the course because it's quite a nice kind of spatial example of some of the processes that we want to analyze. In this case, imagine that we have a set of houses, they all have different values, and we want to basically try and get the weighted average for home values, given the fact that these can differ quite a bit, and maybe our sample is only represented by a couple of houses in each of the blocks. Okay. There are a variety of different kind of preferred measures for when you're trying to measure the central tendency. So for example, if we've got a variable that's nominal, often the best measure for central tendency is the mode, obviously, because if it's nominal, it's categorical. You can't take a mean value from it, for example, or not easily. You could use some count data, but it would be better to try and take the mode here for the overall distribution. For the ordinal kind of variable that you might have, so it's a category, but it has some implied either strong or weak order within it, then maybe the median would be a better way to go. And then for the other types of metrics, whether it's interval or ratio, depending on how skewed it is or not, you might find the mean or the median better. So for example, if it's not skewed, yes, the mean would be a nice way to represent the distribution. But then when we get to a skewed distribution, like the income distribution I showed you previously, the median is actually a far better measure, because otherwise your mean is getting pushed far beyond what is probably the middle point in the data set. Okay. So let's move on now. So previously we were thinking about central metrics to describe a distribution. Now we want to understand the variation that actually exists within a data set or a metric. So the range is something which you may have encountered before. So that's the difference between the smallest and the largest values. So we'll calculate this very easily within the lab, but it's not actually that useful. It just provides us with some understanding of how far, what the distance is in the data set between the minimum and the maximum point. Fine. What's actually quite useful when you've got outliers in particular is to have some understanding of the quantiles. So for example, a quantile is an equal portion of a data set. So if I say to you, I want to set our to divide our data set into quartiles, that means we're going to have 4 equal sets, quarter, quartiles. Okay. If I then say we want to use quintiles, that would refer to 5 equal sets. And before, I previously mentioned deciles in quite a bit of my work, so that would relate to 10 equal sets. And then equally, you'll be familiar with percentages or percentiles. So essentially, that's pertaining to 100 equal sets in this particular case. Okay, and I just missed the median earlier, but I mean, we've covered that already. So we know that to get the median, we would have to sort and rank all of those data points and then take the middle point within the data set. So obviously, if we're going to take the median, then that would essentially be 2 equal sets that we would have for that one metric. Okay. I did mention John Tukey before in the first lecture, and actually I mentioned that he created the box plot, and one of the great things about that is that it captures the interquartile range. So I've just provided you with a bit of an overview of how that's calculated here. I think that what's great about this is it's a way to actually display a lot of descriptive metrics about a single data variable in a single plot, for example. So here we have the median, which is in the center of the quartile range here. So the quartile range is the grey box. So the very top or the bottom of the grey box is the 25th or the 75th percentile. And then we have the mean also shown within this grey box. You can see here it's quite skewed, the data, so the mean is actually quite a bit above the median. And then we have the whiskers as well, which basically start to indicate, I think it's 1.5 times the interquartile range beyond the box there, so the whiskers. And then we also have any potential outliers that might sit beyond those whiskers, okay? So it doesn't connect these in, it's just saying that, okay, these are part of the overall distribution, but they're really not representative of the whole distribution. And that's why this is in some ways a far greater, a more insightful way to kind of characterize the distribution of the data over the range, which I mentioned before. And I said the range wasn't that useful, and this is because rather than using the range, we can kind of capture all of this data in one single set of metrics. So I like box plots, and I think that they're a strong way to understand the distribution of particularly lots of different types of data by the time you start to plot them multiple times. So you can have a full panel plot with potentially displaying up to unlimited amounts of data if you can display it in a sensible way using these particular techniques. Oh, so this is just an example from my own work. So what percentage of annual gross domestic product would each country need to invest in 5G over the next 5 years in order to provide universal service to everyone? So gross domestic product is just the sum of the economic output of an economy. So all of the industrial production, all of the household consumption added together basically ends up becoming the gross domestic product. So it's the relative size of an economy. And the question is, well, okay, maybe you want to improve broadband access. Well, what's the percentage of that GDP that then needs to be invested on an annual basis? So I did this work, and I think I mentioned it before. This is kind of a global analysis where I tried to group countries based on their level of existing development, and I was focusing on mainly low and middle income countries here. So I did some clustering. So I took GDP per capita, population density, 4G coverage. So these are factors which affect how much you can spend on broadband, basically. And therefore, as a consequence, they kind of help us group countries together which have similar characteristics for rolling out 5G. Okay, so similar cost characteristics both for the supply of the infrastructure and for the demand, so the ability for us to actually pay for those services. And once they were in those groups, I was able to basically, for all those different clusters, you can see here C1 to C6, you can see the color schemes are the same. So everyone that's in C1 here generally has quite low incomes. There are a lot of these are Central African countries, all the way up to these countries up here where you have much higher incomes in the group. So it's kind of Brazil, Mexico, Russia, China. So this is the kind of distribution of those data points. And then here what I'm doing is I'm just saying for all these different capacities, different scenarios of capacity, so 400 megabits per second per user is higher than 25 megabits per second per user. And then these are different strategies for how you connect people. So using either 4G with a microwave backhaul or 5G, sorry, or 4G with a fiber backhaul, etc. Or you're using 5G, okay? And the point is that then for each of these clusters that you can see on the x-axis, I'm actually able to show the distribution of those countries within that cluster for how much they would have to invest in terms of GDP per capita in order to provide 5G universal service, okay? So this is a kind of nice way that I managed to use it. You can see that it captures the outliers quite nicely because they're quite distinct from the other kind of whisker parts of the box plots. And then you're also able to get insight into the interquartile range and the median, for example. So these are pretty handy to kind of characterize the distribution that you might have for those countries within these cluster buckets. So let's move on now from the interquartile range. Let's talk about the standard deviation. This is essentially just think of this, that average dispersion around the mean. Okay, so the mean is the arithmetic mean, the average in the data, but then we want to understand how much variation there is around that mean point in the data set. Okay, so the deviations from the mean are squared, then averaged, and then square rooted to put the numbers back into the same units. So this sounds incredibly complicated, and I'm going to walk you through it, and then in the lab we're going to actually do it manually, and I'm sure you will get the hang of how we do this. Okay, so don't be too daunted. I mean, I'm sure you know what the square root is, so that's fine. I think the thing here that looks scary is basically actually getting the sum of squares. So that's basically what we're doing here is we're saying for each of the values in the data set, subtract the mean, and then when we get that deviation, so this is the deviation around the mean, then we square it, and then we use that, we divide it by the number of degrees of freedom in the data set, which is here, so this is n-1, so I'll talk to you shortly about that. And that's how we basically are able to develop the sample standard deviation, okay? And actually to get the population standard deviation, again, it's kind of a notational difference that we have here, but the actual math is going to be fairly similar. So obviously, because it's the population, we're not using x bar. Here we've got mu. That's the way that we represent the population mean. And actually, because the population is much larger, in order to derive this standard deviation, we don't need to do we don't need to take the number of degrees of freedom here. So the degrees of freedom is n-1. Here we're just going to use the number of items that we have in the overall population. And the reason why I will go into this at a later stage, I'll give you a little bit of a demonstration in R as to why with smaller samples, we basically need to subtract 1 from the number of data points that we've got, and that's to prevent us getting skewed results, okay? So incorrect results. When we're dealing with larger populations, we don't need to do it because I'll show you in the lab, okay? So kind of, I hope that this is clear to you. This is the math. It looks, big and scary, but the reality is it's actually really quite easy, and we're going to work it through when we get to the next session in the lab. I personally like to see the math and then like to see how it's implemented in the code. I'm not one of those people who just naturally looks at an equation and kind of gets a feel for it straight away. I just don't think like that. I have to break it down into little parts, and then I have to actually either write it out myself or write it in code to understand what's happening. So that's the way that I'm going to try to teach you. If you can understand the math just by looking straight away at the equation, then that's great. I'm really happy for you. I'm sure you do very well in this course. I'm going to take you through in a much more kind of basic level. I'm going to assume that you maybe don't have a huge amount of math background, and we're going to take this really slowly in order to kind of work out these metrics, okay? So that's the standard deviation. As I mentioned before, degrees of freedom is a thing, and that means that we basically have to divide the smaller samples by n-1 rather than just using the total number of data points that we have in the sample, okay? And I've just provided a bit more of explanation here. When n is over 30, the difference is very small, so it doesn't really matter. But basically when we have small samples, so under 30 data points, for example, the population standard deviation formula is generally underestimating the actual population standard deviation. So we basically need to use a denominator where we subtract 1, okay? And this kind of prevents us biasing the estimation, okay? So don't worry, this is all high level. We'll go through it in greater detail when we get to the lab. Variance, so this is the average square deviations from the mean. So you'll notice that this looks a lot like the standard deviation. Here, remember I mentioned that we are actually taking the square root at the end to put the number back into the same units that we originally started with. You'll notice down here for the sample variation is basically exactly the same calculation. It's just that we're not square rooting it, so we're leaving the value squared, which is why we have s to the power of 2 or sigma to the power of 2 here, okay, for the variance. And again, it's pretty much the same math formula. It's just that we end up having one set of notation for the sample using x bar and lowercase n, and then one set of notation for the population where we have mu as the mean and uppercase n for the population, the total number of data points in the population. Okay, and the point of the variance is just to basically understand the spread of those data points from the average value. And that previous measure here is actually, it's an absolute measure. So that means that it's measured in whatever, it's measured in the underlying data units, essentially. Okay. But the point of using this next metric, which I'm going to touch on now, the coefficient of variation, is that it's actually a relative measure. So what that means is we can take data sets that are actually measured in different units, but we have a common measure here, so we can say how much the data variation is between these two data sets, all right? Irrelevant, regardless of the units that they're measured in. So for the standard deviation, we're talking about an absolute measure of variability, but maybe we want to compare different places in terms of their precipitation amount, or maybe we just want to compare different data sets which are measured in different units. So it's relative. That's the important point with the coefficient of variation. Anytime that you you encounter a coefficient, which you might have done correlation before, you might have touched even on regression, where coefficients are something which you use. You just need to think that this is a number between 0 and 1, and it's indicative of a relationship that we're measuring, okay, in the data. We will go through all of this in this term. You know, regression is the last thing that we get to after 14 weeks or something like that of lectures. So don't be scared. We've got a long way to go to get up to that point. Okay. So essentially, if you've got a low coefficient of variation, it means the data are more clustered around the mean. There's less dispersion. If you've got a high variation, if you've got a greater variation, a high CV, a high coefficient of variation, then you've got more dispersion around the mean. Okay, so the data are less clustered together. And the way that you do this is you basically need to go back, take the standard deviation. So you can see that here, S for the sample, it's going to be our numerator. Here we go, numerator. Then we're going to divide it by the sample mean, multiply it by 100 in order to basically, what we're going to get here, let's just treat it as a percentage. Okay, so it produces a standardized measure of dispersion for a probability or frequency distribution, and I want to present it as a percentage because then you're actually able to interpret it in this way. So when we think about the interpretation, it's easier to think that you know, maybe in this case, if the CV is 0.23, then that's basically 23% variation. And then you can have a coefficient for another data set, which is 0.8, and you can think of that as 80% variation. And then you can compare the two data sets, even if they're in different units, and say the second one has by far more variation in its data points rather than the first one. Okay, so this is kind of abstract. We haven't applied it to anything, and we will kind of get there in the future. But I just need to make you aware that this is kind of a nice measure because it's relative and not absolute. And then finally, just to kind of move on to our last set of metrics, we're interested in the skewness and the level of kurtosis that might be present within a specific data set, a specific metric. So the skewness is looking at the symmetry of the data points in a frequency distribution. Okay, so if the skewness is 0, then just imagine that we have a normal distribution here, and it's kind of perfectly distributed, normally distributed data points, we can call it. Whereas if the skewness is actually below 0, it's negative, then essentially what we've got here is a negatively skewed data set. As you can see, the tail is spreading towards the negative part. So imagine this is an x-axis and you've got a y-axis along here somewhere, and that's the 0 point. And these data points are spreading towards negative numbers. It's going towards the negative part. I think when I first started learning stats, I would always kind of get this confused because I'd always think, oh, but the larger part of the distribution is at the positive side, so that must be positive. No, it's about where the tail of the distribution is. So Imagine it's negatively skewed because that tail is stretching out to the negative part of the graph. And in there, you've got data values. Remember here, we're just looking at the shape, the overall shape of those data points. And that's the part that's negatively skewing the distribution out, okay? And then the flip side of that is that if it's skewness and it's positive, so the number is above 0, then it's positively skewed. Okay, so we can see that down here. Maybe this is actually quite similar to our income distribution. So very few people earn a little bit, and then quite a lot of people earn around this amount, and then actually what you have over here is the Elon Musks of the world, the Jeff Bezos, the Bill Gates, etc., who essentially are earning just ridiculous amounts of money in comparison to everybody else. Okay. And at the bottom here, we have the actual way to calculate the skewness. So we need the sum of, so we need to cube the sum of, it's the sum of the cubed variations. That's essentially what we've got here. So for each data point, we're subtracting the mean, and then we're adding up all those values after we've cubed them, and then we divide it by n times by the standard deviation to the power of 3. Okay, so this is the way that we calculate this metric. Just be aware of it. We'll be able to calculate it in the lab in greater detail. And the skewness ends up affecting the central tendency in a variety of different ways. Okay, so there are some nice diagrams like this in the book actually, and I think it's better than this one that we've got here. So let me just talk you through it, and then you can look at them in the book in chapter, I think it's chapter 2, yeah, I think it will be clearer in there for you. So if we have a normally distributed data set here, the mean, the median, the mode, they all sit on top of each other because you have that perfectly symmetrical bell-shaped curve. The difference if you then have a positive skew, as we had with our income data, is that the most frequently occurring value, the mode, is here at the top of the hump. The mean, because of all of these positively skewed data points, is way over, being positively skewed as well as a consequence, way over to the right here. And the median is then as a consequence in between the mean and the mode. What we have in the case of negatively skewed data is essentially the same, vice versa in a negative direction. So the mode again at the point where you have the highest number of data points, the mean being negatively skewed towards the negative numbers because you've got that long tail in the distribution towards the negative numbers, and then the median obviously in the middle. Okay. And this is just a paper which I did with some of my Spanish collaborators relatively recently. And actually, we were thinking about the distributions in terms of the signals. So actually, this x-axis that you've got here, imagine this is the number of decibels, which is measured on a log scale, that your cell phone is actually able to detect. So we had like a really huge data set. It was like 200 gigabytes. And just for London, we basically took all of the cell phone measurements that we had. And what we did was we wanted to understand by the operator, so Vodafone, O2, E3, just think of this as, you know, AT&T, Verizon, etc. And essentially, we wanted to understand the distribution of those data points. So what we have on the y-axis here is actually the probability. It's giving you a proportion of the samples, but you can think of it as a probability. And as a consequence, that means that you can think, well, I've got a certain probability of the next value that I'm going to get falling into this particular part of the distribution, okay? So if we're looking, let me find a good one. Okay, so let's just go here. So let's say I'm interested in how many signal measurements may be at minus 10 dB. Well, if we look at this point here, and then we go across to the y-axis, we have a proportion of about 0.15 out of the overall sample. So that's probably, so to get a data point that's in that region, a signal measurement in that region, you've probably got about 15% chance. So in geotype 1, so the most dense, the most densely populated area, that's what this represents. You're going to get a cell signal of this potential magnitude for this particular operator. Okay, so that's just a kind of real world example of how we use this stuff in our actual research. And you've got a link down there if you want to go and take a look at the paper. That's open source. You can take a look at the work that we did. It's quite a nice paper. Okay, so that's a real world example. And then the kurtosis basically is measuring how flat the distribution is. Okay, so on that bell-shaped curve, we had quite a nice set of tails coming up to a reasonably pointy distribution in the middle. And actually, you get some distributions that can have really strange kind of dimensions in the upper part of the distribution, and they have all these fantastic names. So platykurtic here, which is negative, so that's a flat distribution. Just think of it in terms of platypus, which obviously is an animal, very flat, and it shares, I think it's Greek, it shares the same name, platy. I think that it's like plateau. I presume that's the semantics of that is that it's like either a Greek or a Latin word for flat, and that's how it's ended up being applied in these circumstances. And leptokurtic here, it's about the peaked, the very, very highly peaked data distribution. So you can see that in this example on the right. We've got the red version, which is highly peaked, which is leptokurtic. We've got the platykurtic, which is the blue line here, so it's very, very flat. And then we've got the mesokurtic, so that's just the normal level of kurtosis that we would expect. Okay. And again, it's quite similar, the math equation that we're going to use, but this time we're actually raising these values to the power of 4. Okay, so we'll go over this in the lab. But just to finish, I just wanted to point you to the fact that there are these things that are called the moments of the distribution, and actually the first moment is basically where we take the sum of the deviations, so that's the mean. The second moment is basically where we take the variance. So this is, you can see we've squared these values here. The third moment is the skewness, which we covered before, which is the symmetry within the data, and that's where we essentially cube these values. And the kurtosis is known as the fourth moment, and actually you can see that here, that we are raising these deviations to the power of 4. Okay. So that's the third lecture. Today I've been covering descriptive statistics, and we've covered a variety of different ones. So we've covered measures of central tendency, we've covered areas of data dispersion, and then we've covered the distribution-focused metrics, which focused on kurtosis, or the kind of symmetry that underlines those metrics. Okay, and we've gone over that in quite a high level. I appreciate that. And now in the next session in the lab, what we're going to do is we're going to actually work out how to calculate each of those. So what I want you to do when you actually come around to revising this is I want you to think of the math equations that you have, both in the book, also in the lecture slides, and then I want you to kind of think about them in terms of then how we calculated these within the lab. You know, I can show you how you do that either in a spreadsheet, but I want you to do it in R as well, so you know how to use both types. And then you can kind of have an understanding for how to do these calculations in your head, which hopefully should help you kind of learn these metrics and then kind of implant them into your long-term memory. Okay, so thank you for tuning in again today to what was the third lecture for GGS300, Quantitative Methods for Spatial Science. I look forward to seeing you all in the lab. Thank you.